This is AP Calculus BC, and in this video I'm going to talk about section 6.4, which is titled The Length of a Plane Curve, and section 6.5, which is titled The Area of a Surface of Revolution. So in these two sections, we're really talking about arc length and surface area, and they're very closely related. So it might seem like a lot of material being presented all at once, but you'll see once you see how arc length and surface area are related, you'll see that it's a very easy transition from arc length into surface area, and it's very, very easy to cover both of these at one time. So when we talk about arc length, what we are talking about is measuring the length of a curve. And if you think about a curve representing the path of an object, then you can see how measuring the length along that curve might be important, because that would tell me the distance something has traveled. And so the way that we are going to measure the length of a curve is actually fairly easy to do, but I want to show you just really briefly where this comes from. So the idea behind this is that when we're trying to find the length of a curve, and you can see this curve over here, we're trying to find the length between point A, where x is A, and this point over here where x is equal to B. If we want to measure along that curve, what we are going to do is essentially break that curve into a bunch of very, very small line segments. And we know how to find the length of one of these line segments because I can just use the distance formula. And that's what we're showing here. If we have one of those small pieces of the curve, it would just be the square root of the change in x squared plus the change in y squared. So now, in order to convert this over to get the exact solution or the exact length of the curve, rather than looking at these large delta x or delta y values, we're going to take the limit as delta x and delta y approach 0, and we're going to sum up all of those pieces. And that would give me the exact length of the curve. Now, there's a little bit of work that goes into this, but we can convert this over into an integral notation. And once we're in the integral notation, that's essentially what we're going to do. And then with just some algebra, and I'll let you read through the steps on your own, but with some simple algebra, we can convert this into the integral form that you see here, where the length of a curve is equal to the square root of 1 plus the derivative squared times dx. Square root of 1 plus the derivative squared times dx. And that's going from A to B. So it's a fairly simple idea, but the main thing is, don't just remember this as sort of a formula that you follow. Try to remember what's actually happening when we solve this integral. We're adding up a bunch of very, very small line segments, and when we piece all of those together and make them infinitely small, we are getting the exact length of the curve. So here's an example of just a very, very simple problem that you might solve. Find the length of the parabola y equals x squared from -1 to 2. And so for my length, all I have to do is integrate along the x-axis. You can see my limits of integration, -1 to 2. And then I need my square root of 1 plus the derivative squared. So the derivative here would be 2x. We square that, and then we're going to plug that into the calculator, and we get about 6.126. Now, on a lot of these problems, I showed this with a calculator solution because on a lot of these problems, in order to get an exact solution, you're going to have to use a method of integration that we have not talked about yet, which is called trig substitution. So I don't want you to get lost in trying to integrate these things out by hand. I want you to primarily just focus on the idea that you can get these things set up and then you're going to plug them into the calculator. It's sort of like when I went through volumes. I don't want your main focus to be trying to solve the integral. I want your main focus to be on arc length. So actually setting up the integral. So keep that in mind. Like I said, a lot of these integrals you won't be able to solve, but even on the ones that you can, it's going to be few and far between. And that's not really what I want you to focus on as you go through arc length and also surface area. Okay, so sometimes when we are measuring along a curve, we might have a function y in terms of x, but we also might have an equation where we have x in terms of y. And if that's the case, we can still find the arc length when we have x in terms of y. And I didn't show all of the derivation of this, but it works out in roughly the same way that if I want to integrate with respect to y, then I can set up my integral this way. So instead of 1 plus dy dx squared, I can go through similar algebra and get it into the form of 1 plus dx dy squared, where dx dy is the derivative of my equation with respect to y. Okay, so here's an example of one that's already been set up. We have, it says find the arc length of y squared is equal to x from 0, 0 to 1, 1. Now, notice we have x in terms of y squared. So if I were to take the derivative here, dx dy, that means I'm taking the derivative of this equation with respect to y. My derivative is 2y. And now notice my setup for my integral, 1 plus the derivative squared. And then this is a y value, my lower value of 1. And this is a y value, my upper limit value of 1. Okay, so pretty simple to do. And like I said, keep in mind whether I have y in terms of x or x in terms of y, I can get the arc length or the length of the curve using either one of those methods. Okay, so sometimes what we're going to want to do is we're going to want to get a representation of the length anywhere along the curve. And that's what this next example is designed to do. So what we're doing here is we're trying to create a function that is measuring if our initial point is 1, 1, how far have we traveled if we're at any other x coordinate along the curve. Okay, so I'm going to go through just my sort of typical process here of finding the arc length. I need the derivative of this function. So f prime of x would be 2x minus 1 over 8x. Now we know inside our radical we would have 1 plus the derivative squared. Well, that means that I would have 1 plus 2x minus 1 over 8x squared. If I were to go through and expand that all out and then factor, and I'm not going to show all that algebra here, but I can go through and I can actually simplify this into 2x plus 1 over 8x squared. Okay, so you can do that algebra on your own if you want, but it actually simplifies down into that. So that means if I were to take the square root of 1 plus f prime of x squared, I'm going to take the square root of that expression, and that's going to give me 2x plus 1 over 8x. Okay, so my distance anywhere along this curve, I'm going to start at 1, and I'm going to go to whatever x coordinate I'm stopping at. Notice that we're using t as a dummy variable. We've discussed that a little bit before. That's just because we're going to plug x into this function, and we want to make it clear that x is plugging into the t, or in for the t. So now my distance anywhere along that curve can be represented as that. And if I wanted to, I can integrate that, and I can get an actual function of y is equal to, let's see, it would be x squared plus 1/8 natural log of x, and then I would have minus 1, and that would give me an actual function. But we're just going to write the function as an integral. And with the function written as an integral, now if I want the length anywhere along the curve, I can just substitute into that. So if I want, for instance here, it says use your function to find the length of the curve, x squared minus natural log of x over 8 from 1, 1 to 3 f of 3. Well, if I want the distance when I'm at an x coordinate of 3, it's just the integral from 1 to 3 of 2t plus 1 over 8t dt, and that would represent my length. And if we actually solve this out, we would end up with 8 plus 1/8 times the natural log of 3. That would be my exact distance along that curve. So the main idea is now I can get the distance anywhere along the curve. If I want it when x is 5, if I want it when x is 4.7, if I want it when x is 1,000.678, it's still the same process. I'm just going to solve that integral. I've got my function defined as an integral. Okay, so fairly simple to do. So main idea with arc length, you've got two setups, and it really is dependent on what information do you have. Do you have y in terms of x? You're going to want to use this setup. Do you have an equation where you have x in terms of y? You would want to use this setup. All right, so let's move on to the idea of the area of a surface of revolution. So this has got a similar reasoning to when we were doing volumes by revolution. So what we're trying to do here is we're trying to find surface area. And in this case, what we're doing here, if you look at this diagram, we've got this curve f of x being revolved around the x-axis. And the surface area that we're talking about is all of the area that's shaded, but we would not be including the two circles at the end. So just the surface that is created by the actual function. That's what we're trying to find the area of. Now, to do this, I told you this was closely related to arc length. Well, notice here what we're going to do. We're essentially going to break this into bands of area. So when I break apart this surface area, I'm going to think of it as small segments along my curve, and then those small segments are going to be revolved around the axis to create rings of material. And then we're going to add up all of those rings of material to get the total. And so, like it says here, you can use thin bands, and each one of those bands, when I measure around it, it's going to have a distance around of 2 pi r, and then the length along the curve would be the other dimension that would give me an area. We're going to call that here dl. So that's a small differential length. And we saw that dl value in the arc length setup. Okay, so in the end, here's how I'm going to set up my surface area. 2 pi is just factored out of the integral, and then I'm going to do the radius times that small arc length, and then I'm going to add up all of the pieces. Now, that dl value, we already talked about when we went through and we looked at this with arc length. We know what dl is. It's the square root of the change in x squared plus the change in y squared, which we then saw also in the last section, how we can convert that into a different notation that will allow us to integrate. And when we convert it, here's what we end up with. 2 pi times my radius times the square root of 1 plus f prime of x squared dx. And we're going to go from, again, a to b in this case, a being the starting x coordinate and b being the ending x coordinate. So if I have my setup where I've got everything in terms of x, I can set it up that way. Now, notice that the radius, the r of x, if I'm going to revolve around the x-axis, that would essentially be my function that is measuring from the x-axis up to my curve. So we're going to go through an example here, a couple of examples, so you can kind of see how to set these up. But the other way that we can do this, if we had x in terms of y, we can still work these out in the same way. The only thing is now I want to have my radius in terms of y, I want to have my derivative dx dy, but I can still work them in both ways, just like when we did this with arc length. Okay, so here's an example that I want to show you. It says rotate the square root of 4 minus x squared from -1 to 1 about the x-axis and find the resulting surface area. Okay, so we're going to take essentially this semicircle, revolve it around. So really what we're finding here is the surface area of a sphere that has a radius of 2. But if I were to take my derivative here, because I know I need the derivative, it would end up being -x over the square root of 4 minus x squared. Okay, so that's my derivative. Everybody knows how to take the derivative and simplify. So for my surface area, I'm going to have 2 pi times my radius. My radius in this case is going to be measured from the x-axis up to that curve. So the radius in this case would be the square root of 4 minus x squared. And then I'm going to multiply by the square root of 1 plus dy dx squared. So 1 plus -x over the square root of 4 minus x squared. And that whole quantity gets squared. And then I've got my dx here. And then from there, it's just a matter of solving the integral. Now remember, we're going in this case from -1 to 1. So we're really just finding the surface area of sort of a strip of that sphere, because we're going from there to there. So I'd go -1 to 1. And then if you wanted to, you could actually solve this one out by hand. The algebra actually works out really nicely. But like I said before, I don't want you to really focus on trying to get all these integrals solved out by hand. I want you to just focus on the setup. And then at that point, you can plug it into the calculator. It turns out for this one, you get a surface area of exactly 8 pi. Okay, so fairly simple to do, because it's almost the same thing as what we did with arc length. You just have to remember that it's thin strips of area or bands of area. If you think of it that way, then you can understand where the 2 pi r is coming from, and then the length is giving me that other dimension for the area. All right, so let's look at another example here. This one's been set up in 2 different ways. And I just want to show you how, even though we've got an equation where we have y in terms of x, we actually have the option to work these in either way. So in this case, we have y equals x squared from 1, 1 to 2, 4 being rotated around the y-axis. And you can see the surface that's being created there. So one way I can do this is I can get my derivative here. So in this case, dy dx is just equal to 2x. And then we take that and we square it, and we result with the 4x squared. Another way we can do this is we can say, all right, if y is equal to x squared, that means x is equal to the square root of y. That would be the part of the parabola on the positive side of the y-axis. So that would be my radius was the square root of y. And if I took the derivative here, dx dy, what I'd end up with is 1 over 2 root y. Now, I didn't show the original form where we plugged this in, but remember, this would be 1 plus this derivative squared, 1 over 2 root y squared. If we go through and simplify that out and work through that whole process and simplify it down, it will simplify into the square root of 4y plus 1. So there's some algebra that would come into play there to get it into that form. But other than that, it's basically the same thing. We're just doing 1 plus the derivative squared, taking the square root of that, and now we're integrating with respect to y. So notice my limits of integration are now y values. From the 0.11 to the 0.24, that means 1 for y and 4 for y. Okay, so again, at that point, you can just plug it into the calculator. So even if you had this second one in an unsimplified form, our radius, you can see in this case, was the square root of y. So the radius would be in there, and we'd have the square root of 1 plus 1 over 2 root y, that whole thing squared. You could just plug it into the calculator like that. It would be totally fine. You'd still get the same result. Okay, so last problem that I want to show you here. It says, find the area of the surface generated by rotating the curve y equals e to the x from 0 to 1 about the x-axis. Okay, so I just want to show you this to give you an example of what might happen if you think that you want to solve these out by hand. So for this one, we're taking the curve e to the x, so revolving around the x-axis. So from the x-axis up to the curve is going to be my radius. So you can see the radius is listed right here, 2 pi r square root of 1 plus the derivative squared. Now, let's say we wanted to try to solve this out by hand. And we said, all right, let's let u equal e to the x, because I think I can do a substitution here. Well, when you do your substitution, you can do a substitution and you'll get an integrand that now looks like the square root of 1 plus u squared du. It's not that that's impossible to solve, but in order to solve that, we would have to now do a trig substitution, which is something that we're not going to cover until next semester. So that's why I'm saying when you get to the point that you've got these integrals, don't try to go through and solve these things out by hand, even though there will be some rare circumstances where they will work out and you won't need anything but maybe like a regular u substitution. I don't want you to try to do that every single time. What I want you to do is set it up and plug it into the calculator, which gives you more repetition on really focusing on just the setup and the surface area and then also the arc length, because that's really what our main focus is here. Okay, so make sure you practice with this stuff a little bit. Once you've gone through a couple of these with arc length and a couple with surface area, you'll find that this setup is very, very easy to remember because they're so closely related.